Hey guys, I was thinking the other day about how back in the day programmers, when they wanted to draw something on screen, they would go directly to memory, and in memory there would be addresses that correspond to pixels on screen, and then they would just set colors for each pixel manually in memory, and then computer would just draw whatever they set there on screen for them. And I was thinking, can we do that today? Can we still program like that in this day and age when we have these high-level frameworks and libraries? Can we still do this hardcore programming? And the answer is yes. Yes, we can. And this is the goal of our project today. Let me show you what we will be doing today. This should be the result of the work that we will do today. This window with a green circle in the middle, and as you can see, we can resize it, and then the circle would scale accordingly. And the interesting part is that we will be implementing this by manually setting color of each pixel in this window in memory, and then we will hand it over to operating system so that it will draw those pixels for us on screen, as you see here. We will be using C as much as we can, and we will be also using a little bit of Objective-C because we will be dealing with macOS APIs, but we will try to use as low APIs as we can so that we can do as much as we can by hand. First, let's create the XCode project here. Okay, so let's do macOS app. We want storyboard, Objective-C. Let's do low level rendering. How about that? Okay. Alright, good. We will keep all the stuff that we got here. And we have this view controller which lets us have a handle of a NS view, and this NS view is the interface that represents the view on macOS system. And it's important to us because we need to somehow get a handle to the window so that we can render there, and NS view is the way we can do that. So we need to understand how we can get a handle of all the pixels that compose the window that we can create. And so it turns out there is this drawRect method here which draws the view and its contents on screen directly. And so the approach that we can take is by subclassing the original NS view, and then we can put all the drawing logic inside this drawRect method. So let's start with that, and we'll see how it goes. So the first thing is to create a new header class for the view. In our case, let's call it custom NS view. We'll also create the Objective-C implementation file. We don't need that. Can just do this. Then here we can declare new interface, in our case custom NS view, and subclass it from NS view. And we also need to import, I think it's AppKit NS view. Yeah, so that's the one. And so now in our implementation file we can start implementing things. So we were saying there was this drawRect method that we need to subclass. Okay, void draw rect, here it is. Okay, so this is the method. Basically, for original view, this method is going to be called every time the view contents need to be rendered, and it's all done automatically, and we want to change that logic because we want to decide what we're going to draw and how and when all by ourselves, and that's why we created this child class for the NS view so we can put our logic inside here. Let's now put some logging statements to see how often this method is going to be called. Let's say inside draw rect. Then another important thing is that we now need to go to our storyboard, and it already has some stuff configured for us, and in this view controller scene it already has a reference to whatever view the application is using, and by default it's using NS view, and we must specify our custom NS view so that it can be used. It's a little bit crazy, but it's all Apple specific stuff, so have to do that. And so now we did that, and you see how the view changed to custom NS view. So it means that now if we run the application, then this is the view that the application will be using. So let's see if that is the case. Let's try to build and run it and see what we get in the console and what we get on screen. Okay, we got this window created by operating system for us automatically. Right now it's totally empty, and let's see here. Okay, we get these print statements here, but there's quite a bit of them. Hold on, let's rerun it again. Don't touch the window, and so by default you see draw rect was called twice. It's kind of weird, why not once, but I think we can live with that if it's going to call it twice just at the initialization. And then we got a lot more logging statements, and I think that's because I was resizing the view, not the view. And as I was resizing the window, I got more draw statements. So we can conclude that basically this draw rect method is going to be called when the application starts to render the stuff on the view initially, and then every time we get this change window size event, then this method is being called again. So I think that's probably fine for the moment. Let's now think about how we can get a hold of each individual pixel on this window and how we can set them. So there is this CJ image ref class which represents a bitmap image, and bitmap image essentially is a region in memory where colors for each pixels are just stored contiguously row by row by row in different formats, and typically each pixel is represented by 4 bytes for red, green, blue and alpha components. So this is the class that we can use, I think, for our purposes, and we can use it in our draw rect, right? So the logic should be something like this. Let's start studying it here. So first we will have some image which will represent the region in memory where we will put color of each pixel for our window, and then we will need some sort of way to hand this image over to operating system and ask it to render it for us. And so the way we can do it is by using the CG context draw image. And all these references that I show you here, notice that this is all part of core graphics, and this is lowest level APIs that Apple has. This is all C stuff, old style C, and it has been developed basically a long time ago, but as you can tell by all the versions here. So it's very old, very low level stuff, exactly what we want for this project. So this function here, it says draws an image into a graphics context. Okay, so image is this bitmap that we saw earlier, this one. And then there are also this notion of graphics context. And this is a fancy way of calling the region in memory again with some pixel colors. So in our case, it seems like if we can get a hold of the region in memory which operating system allocated for this window, right? So when operating system created the window, it must have already allocated some region of memory so that colors of each individual pixels here can be stored. And so if we can get a hold of this region in memory somehow and then put our image there, then we can assume that maybe that will work, and maybe then operating system will draw it for us. And as you can see here we need to get a hold of this graphics context, which is again the region in memory that represents the window that is already created for us. And then we also pass an image that should be put inside this context, basically that should be rendered to this context. And then we also need to specify the rectangular area to draw this image to. So effectively we need to say which part of this window should we draw this image that you're giving to. Do we want just some part of window or maybe entire window? So that's why we have this rectangular CGRect structure here. And so that's the method that we will be using. So CG context draw image. And so again, we need to get this context, which we don't have, rectangular area, which we can create it. Let's assume that we will be drawing to entire screen when, let's say, when we are in full screen mode. So we need to somehow get a width of height of the current screen. We'll deal with that a little bit later. And then there is the CG image ref pointer to our image, and we will already have it by now. And then now we need to get a hold of this graphics context that represent the current window. And there is this nice API that Apple has for that, NS graphics context. And whenever you see this NS prefix, it means that we're dealing with macOS, because for iOS it's different stuff, different set of APIs. It says graphics context as a destination to which drawing and graphics state operations are sent for execution. So in our case, we want graphics context associated with current screen, and this current context is the property that we want, current graphics context of the current thread. The way we can get a hold of that is, so we want CG context ref type to match this one. We'll call this current context, and as graphics context current Kate doesn't have autocomplete because I need to import it. Where it is, it's AppKit again. Okay, AppKit, and as graphics context, that's the one. Good. Current context, and we want, and by default, okay, it doesn't see that, but it's a pointer to NS graphics context, and we want CG context ref. So there is a nice helper which we can use to get the pointer converted to this core graphics type that we want. So that should do it for us. We will pass it here. Then we should go back and see how we can create this image, which is essentially a region with pixel colors that we want to draw. We need CG bitmap context create image. Yeah, naming is kind of crazy, but what can you do? So it says create and return CG image from the pixel data in a bitmap graphics context. So it looks like it's not that simple, right? We can't just pass in our array of pixels here because this method expects us to give some sort of CG context ref. So we need another graphics context to give it so that it can create image from that. Essentially, this graphics context is the actual handle to the memory region, and what this method does, it simply takes whatever data in that memory and just, wraps it as a CG image, essentially. So it's basically you give this method the same memory, but just with a different handle, and it just takes that and puts another handle on and gives it back to you. So that's kind of how I think about it. So anyway, we can use that context create image, and so now we need another context here, and the way we can get that one is by looking at this bitmap context create. It says creates a bitmap graphics context. So by the function definition here, we can finally see that now we are actually getting out of the weeds of this core graphics APIs, and this seems to be the actual method where we can just pass a pointer to the data with pixel colors that we can create manually, and then from there it can do its thing and gives us all the handles of the right types so that we can actually hand it back to operating system. So let's try this one. Let's CG context red bitmap context, and that was bitmap context create, and there is quite a bit of things that we need to pass here. So first of all, let's define what data is. And like I was saying, our data is a set of pixels, and number of pixels is basically screen width by screen height. So we need to have some way of getting the width and height of the current screen. And there is this struct again, CG size, which is basically just a wrapper over width and height. So we can use that one, and there is this NSScreen class which says object that describes the attributes of a computer's monitor or screen. So we can actually use that one for the screen dimensions, and it says dimensions and location of the screen. Okay, cool. Frame size. Okay, so that should give us the current screen size. Okay, and of course we need to import that as well. That's going to be a screen. And so again, this app kit, this essentially contains all the APIs for macOS. If you want to do the same thing on iOS, then you need to use UIKit because it's separate APIs. But this core stuff, CG, it's all platform independent, low-level APIs. So they're going to stay the same. And now that we got it, we can define our pixel data. And the way we are going to be doing it, there are multiple formats for pixel colors, but the one I will be using here is this RGBA, where you have a 4 bytes representing color of a pixel. And so 1 byte for red component, 1 for green, blue, and alpha. And this should give us the understanding of how much memory we need to allocate to enough so that we can store there all the pixels that we need for screen. And that would be, say, let's do size t bitmap size, and that is, since each of this RGBA is just 1 byte, so I'm going to be using this uint8t type, so size of 1 byte times 4, right? And that's going to be, this one is going to give us the size of memory for 1 pixel, and then we have number of pixels, screen size, width times screen size height. So this is how many pixels we have, and this is how much memory we need for 1 pixel. So this in total should give us the total number of memory that we need to allocate to store entire bitmap there. And now that we did that, we can allocate the memory. We are using seal, so let's do malloc, let's say, and then we can pass it here, bitmap data. Okay, so width, in our case we want screen size width, screen size height, and then bits per component, that's 8, right? Because component, it's one of those RGBA, each of them is a component here, and we said that it's going to be 1 byte per each, and there are 8 bits in 1 byte, right? So that's why we put 8 here. And then bytes per row, so in our case row is going to be width of screen, that's 1 row, and this is how many pixels, and each pixel is 4 bytes, so we need to multiply that by 4. And then there is this CG color space ref thing. So for that, that's the page I was looking for. So essentially Apple says they support different color spaces, right? Like RGB, this one, and grayscale. So in our case we want to be using RGB, and so out of all those methods, like the simplest one to use that should give us everything we want is the CG color space create device RGB method function. And it says we also need to manage memory for this stuff as well, so that's good to know. Okay, device RGB. So let's create that one, CG color space ref color space, CG color space, create device RGB. Okay, fix typo. Okay, so it said what, CG color space release. Okay, let's start putting this cleanup statement so we don't forget. And here that would be color space, and the last thing we need to do is this bitmap info. Let's see. bitmap info. So I happen to know that we can search for CG bitmap info here. It says component information for a bitmap image. So here we can do a number of things actually. I think I might show you this in code actually. So if you go here, you see there is this set of enums. We can use them to define what is the byte order in our bitmap data, right? You see it says just RGB without alpha and then RGB with alpha in different orders and whatnot, and pre-multiplied, non-pre-multiplied. So there is a bunch of things. Also, what is the byte order? Is it little endian, big endian? Lots of things. Actually, what's interesting is that this bitmap info is just a 32-bit unsigned integer. And so you set the configuration in this hardcore C style where you just set specific bits in that integer to whatever values are listed here, and depending on them, API will understand what type of data you have. So there is this really useful... Okay, so yeah, here is the page I was looking for. So essentially it tells you what combinations of these enums are supported at all. So it says 8, I think it's bits per component. Yeah, bits per component BPC and bits per pixel. So in our case we are using RGB, and as you see there are like different color spaces, right? Like we're saying grayscale, this one, and then RGB. So we're using RGB and we have 32 bits per pixel, right? Because 4 bytes, 1 byte per component, 4 components, that gives us 32 bits per pixel. And bits per component 8. So in our case we do 32/8. So we need to select one of these 4 effectively. And in our case we will be using alpha as well. And these 2 without alpha, so and alpha comes pre-multiplied first or last. In our case it's last. We should be using this one. And what's interesting is that this is actually default. So all we need to do for the bitmap info is to set the bit that corresponds to this, to where the alpha component is in our data. We can do it pretty simply actually. We can just do kcg alpha pre-multiplied last, right? Yeah, that's the one we need. Okay. And then that's all. What should happen is that it should just take our data, bitmap data, and give us a wrap it with bitmap context and give us a handle to that. And now we can just pass it to this function here that should give us a different handle, CG image ref, that we want. Okay, bitmap context. Okay, it doesn't like this one, I think. Yeah, that's... Oh, okay, yeah, I made a typo. Okay. Good. So now we need to pass the width and height of the screen, and we got them just above screen size, height. That's looking really good. So we got through the weeds of these low-level Apple APIs, and hopefully it makes sense for you guys. So let's talk about it a little bit again. So we have the screen size, which is how many pixels we have on the main screen currently, and then we just allocate enough memory so that we can store colors for each of these pixels in the screen, and each color is stored as a 4-byte component RGBA, and then we create a bitmap context, which is essentially we wrap our raw pixel color data with some Apple wrapper that we need to use their APIs, and then we exchange this handle for this handle later. Then we get handle to the region of memory that is associated with current window, so that we can take our image and draw to our current window, and then we actually call this draw image method, which actually does the drawing. Then we need to do some little bit more of a memory cleanup. So let's do that. CG context release. So that's our context we're creating here, then color space, and then we do free bitmap data. That's the raw data that we allocated. And so notice how I'm doing it is like a reverse order of allocations, and I don't think that matters, but I just like to do it to satisfy my OCD. Now if we run this, what we will see, what will happen, right? Let's see. Oh, cool. Got some nice, really nice looking stuff. Very nice help. A message here. Okay, so it's actually working. I bet it's difficult for you to say that it's working, but it's actually working. So reason why we see this garbage is we're actually drawing whatever garbage I have in my computer's memory, because when we do malloc, it allocates enough memory for all this data, but it doesn't really initialize any of the data it allocates. So we have just whatever garbage was there in that region of memory, we just display that, and as you see, it's interesting. And we can actually make it a little bit nicer if we just, let's say, if we use calloc, let's say, right, where the difference with malloc is that calloc will actually initialize the memory upon allocation, right? And so now you see it initialized everything to 0, it seems, so including alpha components, and so everything is just transparent effectively, right? So that's why we don't see anything at all, not even black screen, because again, alpha component is also going to be 0, so this is going to be just transparent. That's why we have nothing. But calloc, I think in this case, I kind of don't like for performance reasons, right? Because we have this extra iteration over all the pixels to initialize them to 0, I think. So I don't like that, because we will be iterating over pixels anyway to set their colors, and so we might do initialization for them at that moment as well. Let's iterate over all the pixels and just let's render like a green screen to start with. So how we can do that? So let's say we're going to do kind of how C++ iterators do it, where we will have like a starting pointer pointing to the start of the bitmap data, and then we will keep going byte by byte until we reach end, which we currently don't have defined, but we will do that, and then we will just go byte by byte, basically starting from the first byte of the first pixel and till the end. And we'll do some initialization here. First we need to define this end effectively, and that's going to be again pointer to the byte after the last byte of the last pixel, essentially, right? So that's going to be this one. And so now let's just start with setting a transparency byte alpha component for each pixels to 1, so that at least all pixels are being rendered as opaque. To help us with this pointer arithmetic, let's draw this helper. So let's say bitmap data starts at offset in memory, let's say 3, right? And then you have all these bytes, and let's say we have 2 by 2 screen, for example. And then, right, so let's say if we were rendering 2 by 2 screen, let's say, then our bitmap data would be stored in this memory region, for example, just for simplicity, so we can figure out the math here. And so I'm going to use brackets to define the different pixels. So this is the third pixel and this fourth, so like 2 by 2, right? So this is 1 pixel, right? 4 bytes. This is red. That's actually right, that one. So let's say red, green, blue, alpha, and so on and so forth. And so let's say what I want to do now in our for loop, I'm going like byte by byte, right? So what I want to do at the moment is to just set alpha of each pixel to be 1, or in our case it's going to be 255, because we by default, again, API is assuming that you're using actually integers and not floats, so that's why your colors are not from 0 to 1 but from like 0 to 255 basically. And again, that would be, if we wanted to change that, then we would go to this bitmap, CG bitmap, what was it? CG bitmap info, and set different bytes, so to use floats. So just so you know. So the way we can do it is to basically calculate the offset of the let's say so that should give us this. Then so let's see how it works. So let's say I'm here, then my calculation here, what this one is going to resolve to is going to be 6 minus 3, right? Because bitmap data is the 3 plus 1, then modulo 4 equals 4 modulo 4, right? And this modulo, it gives you the reminder of deletion, right? So you divide 4 by 4, there is no reminder, so this is 0. And so that's exactly what I'm testing, right? Because if I'm currently at a byte that represents alpha component of a pixel, then the reminder result of this modulo operator will be 0. And so that way, this if statement here, it selects the alpha component, and what I'm doing then is that I'm just saying, okay, so this is the pointer to alpha component, and then I just dereference it and set the value to 55, because that's what I said I wanted to do, right? So let's run it. So now we kind of see, I think, actually I think we see more stuff, right? Because now all the pixels at least are not transparent, right? Because previously we didn't know what was alpha, right? If it was like larger than 255, then or I mean 0 or less than 0, then we didn't even see them here at all. So now we see more stuff, and we just generally want all alpha components to be 255 so that we actually all pixels are opaque. That's what we want. And then how about now we just go there and we set for all other pixels, just set their color to green so that we can render green screen, let's say. Just in general, I think we can iterate over just the first component, first byte of every pixel, and then if we know that we have a pointer to the first byte of every pixel, then we can just set each component, because we know offsets already. We know that there are only 4 bytes for each pixel, so we just can set every component. And so the way we can do it, I think, is just by this, right? So let's say if I'm 7, then I do 7 minus 3, it's 4, right? And then if I do, and 4 modulo 4 is 0 as well. So this should give me the selector. This should give me just basically P is a pointer to R component of a pixel all the time inside this if statement. And so now I can just do something like, I want to set this to 0. This is red component, green and blue. Okay, so how about this hardcore C for you guys? So what happens here is that here I'm just setting green and blue components to 0, red and blue, and green to 255. And so the way it works is that, let's say for this statement, it is the equivalent of 2 statements. So first would be to this one, and another one would be this one, right? So this is just 1 line, this is 2 lines, these 2 lines are exactly equivalent to this, and what it says is that first it sets value of this pointer points to 0, and then it increments the pointer so that now it points to second byte. So if it was pointing to red, then it will set value of this red to 0, and then it will increment pointer so that pointer now points to green one. And you see how that works, right? So that's some cool C stuff that I really like. And then same thing here, set green, move to blue, but then just set blue and don't increment it. And we don't increment it because we are inside for loop. So this last increment will be handled for us inside this by the for loop itself. So that's why we don't do this here. And so now if we run this, we should just see green screen. Yeah, exactly, right? So that's how cool is that? That's really cool. And you see how it's already kind of being scaled for us, right? Because we set the screen size is assuming that we are full screen like this, but when we resize the window, then operating system automatically kind of downscales the image that our bitmap represents to match whatever size of the window that we have. So that's really cool. And then, so now we can actually move on to implement this functionality with circle that we wanted, right? Where we wanted to have this green circle in the middle of the screen. So now it's time for some linear algebra for you guys. Let's do some drawing here. So let's say we have a circle, right? And I probably want to make it transparent like that. Maybe change its color as well, say green. And so what we also have is this pixels, right? Which are kind of little squares, but like not really, right? Because pixel is just essentially sample in the center of the square, right? Not the square itself, but they kind of being used interchangeably. But yeah, for our case, let's assume those are like let's say little squares. And so we have them kind of like that, right? Like row by row. And so okay, let's just do that. And so here somewhere in the middle we have the circle radius, right? Let's have this little point, let's say somewhere here. Yeah, can I make it even smaller? It's probably a small. Yeah, so let's say this is like a radius, right? And let's put some text here. So it says, and it's going to be in the middle of our screen, right? So the x and y coordinates of the circle center are going to be like width divided by 2, height divided by 2, right? So this is the x and y coordinates of circle center, and then we have individual pixels. And so what we want to do is to create like a vectors, and that's a very nice very nice vectors. That's even better. Okay, let's say, how about this? Okay, and each pixel is going to have like a coordinate as well, right? So let's say current pixel x, current pixel y. Those are like x and y coordinates of every pixel. And so as you can see here, if the pixel is inside the circle, then length of this vector between from circle center to the pixel center, then length of this vector is going to be equal or less than the radius of the circle, right? So if that condition holds, then it means that pixel is going to be inside the circle, and so we need to paint it green. Whereas if the length of this vector is greater than the circle radius, then the pixel is going to be outside of circle, and so we need to paint it black. So that's what we are going to be doing. And so the question here that remains, how do I actually compute the length of the vector? So generally speaking, you're going to have like a SQRT of sum of squares of coordinates, right? So you have vector with x and y coordinates, and then you do this and you get the length of the vector. Let's say, how do I get x and y coordinates of this vector? Effectively, in our case, we have the origin of everything located in the top left of our screen, right? That's where 0, 0 is. And so geometrically, like in linear algebra, the vector is just represented by direction and length, and where it starts doesn't matter. So in our case, it's a little bit difficult to calculate the coordinates, what is the x and y coordinates of this vector, because it doesn't start in the origin. But what we can do, we can just, let's say, if we were able to translate the vector to origin like that, then we would be able to much easier see the what is the coordinates, right? Because then the coordinate would be, this would be the x coordinate and this would be the y coordinate, right? Kind of like that. So let me show you. So like this is like the x, right? And basically this is the y, right? So assuming that you have like a x and y like that, then you should be able, you see how it's much easier, right? This is like the x value and this is the y value in this case. And so basically it sounds very complex, but actually to translate the vector and get the coordinates, you can just do basically current pixel x minus width divided by 2. So that's going to be the x coordinate of this vector. And so like this subtraction that we're doing, like geometrically what's happening is that we're just taking this vector, translating it to the origin, and then just taking the coordinates, this coordinates, this x and y coordinates as we draw on screen. And so, you know, mathematically this translation, this process is just subtract the coordinate of a start of a vector from coordinate of a end of a vector, essentially. So that's what we are doing, divided by minus height by 2. This should give us the x and y coordinate of the vector, and then we just apply this formula to this coordinate and we get a vector length, right? So kind of a lengthy explanation, but I hope it makes sense and clarifies things for you guys. So let's now just implement this logic in code. So we don't need this stuff at the moment. Let's start by, let's say, coding, say, current point x, right? So basically the coordinates of current pixel. How do we get that one? And so it would be p minus bitmap data divided by 4, and then size width. So let's see. Yeah, it's screen size width. So let's see how that. Okay, yeah, it wants them to be. So this is basically float by default, but this is long, right? So it wants to have modulo operator applied to same types, and we can now safely convert it because we know that this is like an integer actually, like always. I mean, in our case. So let's see how that works. Let's do some math. So we already know that whatever p we have is going to be the pointer to red component of some pixel. So let's say I'm at this pixel I'm at 11, right? So I do 11 minus 3 divided by 4, so you get and then you do modulo screen size width. And so in our case, if in this case, right, that we testing here, width is 2 and height is 2 as well, so screen size width would be 2. And so what we're going to get is this 8 2 modulo 2 is 0. And so this is actually correct, right, because we are looking to get the x coordinate of a pixel. And so in this case, for every row you have this x coordinate for this pixel 0, for this one, for this 0, for this one again. So for this we expect to have x coordinate as 0, and in fact we get this as 0 by using this formula here. So that's good. So now we can do same thing, current point y, p minus bitmap data by 4, and then I should just divide it by screen size width. So let's see on the example how that works as well. So let's say I now have this pointer to this 15 byte. So what I'm going to do, 15 minus 3 divided by 4, and then divided by screen width, which is 2 again, so you get 12 divided by 4, 3 divided by 2, and that should give me 1, right, because we are doing integer division. So that should give me 1, and again, that's exactly what I expect, because y coordinate of this pixel is 1, right, because y coordinate of this row is 0 and y coordinate of this row is 1, right? So I hope you see how that is coming together. Let's we need to do the vector length calculation somehow. So let's just do the helper function for our purposes. Let's say get vector length. Let's say we get 2 floats, and what we need to do is to do sqrtf, right, like we were saying, and we need to take basically square of x plus square of y. So let's now apply it here. So that's going to be get vector length, and now we need to subtract things, right? So we need to do current pixel x minus screen size width divided by 2, and similar thing by for y coordinate as well. And then another thing is that we need to cast them to floats, because that's what we need for this get vector length. So let's do this cast here as well, and then this cast here as well. Right, so, and now we need to also define what is the circle radius. Let's say, let's just define it here. So I have quite a large screen, so I know, how about 500? Sounds good to me. So can now say if vector length is less than or equal to circle radius, then this pixel must be inside circle, so we need to paint it as green, right? P plus plus 0. So it's kind of the same thing we were doing earlier, and so that should do it. Let's run it and see. Okay, we get some horrible horrible results, and so actually that's because, like I was saying, malloc, it doesn't initialize memory that it allocates, and so in our case we only draw basically initialize bytes that represent alpha components or the inside of the circle itself, but we don't initialize like the rest, and we actually need to initialize the rest to be 0, right, so that we don't draw garbage from memory, we draw just plain black, essentially, right, in both of these situations. And so that should, okay, that doesn't give us anything. Okay, so I actually spent quite a bit of time debugging behind the scenes, and essentially the problem was that I forgot this else keyword here and so because of that it was not actually working. But so now that it's here, and if we run this, then we see the circle is just that it's quite large actually. I think we need to lower the radius a little bit, and now see it's looking much better. But yeah, so the problem that we currently have with this is that it's actually always, when we scroll the window, it doesn't automatically scale the content that we have according to window. It's always displaying the pixels as is, basically, right? So it doesn't scale anything at all, and that's not what we wanted. So let's first look at the documentation for this draw rect function. Draw rect and this view. Alright, so it says dirty rect, a rectangle defining the portion of the view that requires redrawing. What's interesting is that right now we don't use this dirty rect anywhere at all. When we actually drawing the image, remember there was this parameter that specified rectangular area that we need to redraw. And in our case, we always specify the entire screen. And so that's the problem, right? When we run this, no matter what is the actual size of the window, which is represented by this dirty rect, no matter what is the dirty rect, we don't use it, and we always just draw same rectangular area, which represents the entire screen. And that gives us this kind of effect that we see here. And so if we were to replace the thing with the dirty rect, then and run this, then as you see, that's just simple fix to our problem here. And the way it works is that since dirty rect has the size of the window, then operating system automatically takes our image and downscales it to fit inside the dirty rect, which has the size of the window. That's why it's working. We are leveraging this automatic downscaling of our image, which I think is actually pretty cool. Another problem that we see here is that I would say the circle is a little bit pixelated around edges, as you probably see. We can maybe make it bigger, that will be more visible. Yeah, you see how like the edges are a little bit more pixelated than what I would like. This is because we are not leveraging the Retina screen in our application. So effectively what Retina does is let's see here. Right now my resolution is 1504 by 846. And so what's interesting is that this resolution, it actually in logical pixels, right? So this number of pixels is logical, but the actual number of pixels that screen is capable of, I mean, if you use a Retina screen, that would be like 4 times more than that, right? Because in Retina technology, each logical pixel is backed by 4 actual physical pixels. Our screen, well, at least my screen, because this Retina screen, it's capable of much more than just the resolution that we currently have. Right, so let's put a breakpoint here and step in to see what is the screen size. So you see the screen size that we're currently doing is 1504 by 846, which matches exactly what we see here, and this is size in logical pixels, but in reality, number of pixels that screen can handle is 4 times more than that. What we can do is to increase our bitmap size to match the resolution that Retina screen can have. So there is this API that allows us to get the actual number of pixels that Retina screen supports, because right now we just getting a number of pixels for non-Retina screens. We want to have some sort of API that gives us how many pixels we would support as a Retina screen, and so we can do that if we use this NS screen main screen, convert rect to backing, and then again NS screen main screen frame size. Some crazy Objective-C syntax here, but it works. And so now if we do the debugging, we see that it's like now 3008, width and height 1692, and as you can see, this is actually double of this. So what happened is that API scaled the resolution by 2 across x-axis and by 2 across y-axis as well. And so now each logical pixels is represented by 4 actual pixels. That's because my screen currently supports, my screen is the Retina screen. And what's good is that this is actually it's a bulletproof API, right? Because if you're using non-Retina screen, then it will also give you the correct result for non-Retina screen as well. And so now if we run this, then you can see how much more smooth the edges of the circle are. And so we implemented this hardcore application where we by hand specified the color of each pixels on the screen to draw a circle, and we used some linear algebra as well, which is really cool. And then we even got a very thorough deep understanding of what's the difference between Retina screens and non-Retina screens, how it all works, and what are the image differences on both types of screens. And I think that's a lot of really good learning, right, that no high-level API can give you if you don't look under the hood. So I hope you learned something here, and I'll see you the next time. Thanks, bye.